Before we begin, this is a Holden Commodore VF2 SSV sedan with a 6.2 litre Chevrolet LS3 V8 engine. The Commodore was one of the most popular motor cars in Australia from 1979 all the way through until it ended production in 2017. Over the last 15 years, I've owned several of these vehicles with a variety of performance options and enhancements. I even learned to drive in a Commodore that was one of the first 5 production V8 units built on Australian soil. Unfortunately, the factory ceased production in 2017 and these amazing, technology-filled, high-spec performance muscle cars can no longer be purchased. The Holden brand no longer exists. The vehicle pictured here was one of the final cars to roll off the production line. The last 2 that rolled off on the day were also red. The final car, purchased by an ex-Holden employee for around 74,000 Australian dollars, and which had been carefully stored and not driven, was recently auctioned off in Australia for a mere $750,000. Not a bad return on his investment of a little over 3 years in storage fees. This talk presents the findings of recent research conducted as part of the ISAC project, in collaboration with researchers from the Safe Air and Engine B projects, all of which are exploring issues and solutions relating to the legal environment, security and safety of AI and autonomous systems. First, we'll look at some of the legal background for motor vehicles generally. Second, we'll consider how existing law impacts on the technology of autonomous cars. Third, we'll present the processes and artifacts described for deconstruction of traffic law for use in development of autonomous vehicle technologies. And finally, we'll report on a set of road tests conducted using 3 different cars with varying levels of technology in order to evaluate whether existing cars can comply with traffic law. When powered vehicles first hit the roads at the beginning of the 20th century, they brought in their wake major changes to the law. Road traffic law emerged as a legal field in its own right. Today, a wide array of legislation, regulation and standards ascribe complex legal responsibilities on manufacturers, importers and distributors, owners and vehicle users. Soon, 2 complementary sets of rules evolved. One set is directed at the manufacturer of cars, the other at their drivers. Rules impact elements of the design, materials and manufacturing processes. They set minimum standards for safety and protection of occupants and other road users, both in actual and potential accident situations. Separate rules regulate how and where we use our vehicle, and they impose requirements on their maintenance. This separation of responsibilities benefits both drivers and manufacturers. Let's take the example of your vehicle's brakes. Now, their design and manufacturing is covered by a detailed set of rules that happens to include the rather succinctly named Commission Directive 85/647/EEC of 23 December 1985, adapting to Technical Process Council Directive 71-320-EEC on the approximation of the laws of the member states relating to the braking devices of certain categories of motor vehicles and their trailers. Now, doesn't that just roll off the tongue? It is the shared duty of the designer, the supplier who manufactures the brakes, and the vehicle manufacturer who integrates them into their car to know and adhere to such rules. But this is also where their responsibility stops. For they need not ensure that the driver actually uses the brakes when, and only when, it is appropriate. Drivers are in turn subject to road traffic law that requires they drive with due care and attention. This includes a duty to brake when necessary in order to prevent a collision, and not to brake unnecessarily when it may result in one. So, not randomly stopping when driving at speed on the motorway, for example. The driver's task is to make correct and appropriate decisions regarding when to brake, without a requirement to understand the minute details of how their brakes work or whether they can rely on them. Recently, the UK Department of Transport ran a public consultation on the safe use of automated lane keeping systems on Great Britain's roads. An appendix to the department's report proposed monitoring and control tests for autonomous systems. As can be seen, these tests assert that autonomous systems in vehicles should comply with the relevant traffic rules. While inconsistent with the large number of researchers who feel legislative change is needed, at least to enable safe adoption of autonomous cars, this compliance requirement is in keeping with the findings of a smaller group who believe that any issues arising from autonomous cars can be dealt with by our existing legal frameworks and legislation. However, it is not straightforward to anticipate how the law might have to change once the driver as the primary target of obligation is replaced by an AI. The aim is, as the UK government expressed, to have a car that abides by the relevant law. But due to the obvious gap, it's not straightforward how compliance with laws from the set currently directed at human drivers can be subsumed by the set that have prescribed the design decisions. For some laws, the answer is simple. For example, human drivers are currently prohibited from speeding. For the self-driving car, this simply means their AI must be able to ensure that the car remains within posted speed limits. But how should we think about rules like Highway Code Rule 161, which prescribes that all mirrors should be used effectively throughout your journey? Mirrors are a design choice. They're based on human requirements and the fact that our two eyes have only a limited field of vision. For autonomous cars, this rule may not even be necessary, as their sensors can look directly behind the vehicle or into those areas that constitute a blind spot for us. Is it therefore still necessary to attach mirrors to the autonomous car? Also, we see rules where the legislator will have a choice. During the field tests that we conducted, we looked in particular at the rule that currently obligates the driver to ensure that the seatbelts of any children in the car are fastened and remain so. With the driver removed, who, if anyone, inherits this obligation? One answer could be that the law-compliant self-driving car should check the status of the seatbelts and simply stop driving if they're not fastened. But we can also imagine that the duty might be transferred to the next responsible adult, even if they too are only a passenger. The most significant advances for enabling autonomous vehicles have been the advanced driver assistance systems. ADAS are technologies that improve or automate a function of the driving process previously performed by the human driver. The taxonomy used to classify and describe ADAS is the Society for Automotive Engineers Automated Driving Levels. This 6-level taxonomy describes ADAS driving automation based on each technology's ability to automate and subsume the driving task. Levels 0 to 3 are differentiated by who controls two factors, which the SAE refer to collectively as the dynamic driving task. First, vehicle motion, and second, object event detection and response. Levels 4 and 5 are differentiated based on whether the ADAS feature is capable of automation unrestricted by conditions imposed on or arising out of geographic, road, environment, traffic, speed or other limitations, which are referred to as the operational design domain. Level 4 allows for automation constrained by one or more of these limitations, at which point the driver must take control of the vehicle. Level 5 allows complete autonomous system independence. Two motivations exist for this work. The first was to identify a process by which we could get from the legalese of legislation and regulation to rules or conditions that could be embedded in AI and verified in the decision-making of autonomous systems. The second was to perform some simple monitoring tests as proposed by the Department of Transport's report, and to evaluate whether existing ADAS and autonomous systems were currently capable of adherence to the road rules. Our process for deconstructing legislation for use in development of AI involves 3 steps that produce artifacts that represent the structure and rule of law in forms that are more comprehensible for developers and computers. Step 1 uses approaches similar to those of the plain English movement to represent legislation and regulation as structured English rules. Step 2 then represents these rules as mathematical equations. And finally, Step 3 develops law maps, a visual representation of the structure, decision processes, potential paths and outcomes that the law provides. We will now look at each of these in turn through the case example of UK seatbelt law. Any deconstruction process begins with a review of the relevant legislation or regulation. In this case, we begin with the various law that provides rules requiring the use or exemption from use of seatbelts, the most obvious being the Motor Vehicles Wearing of Seatbelts Regulation of 1993. The UK Highway Code Road Rules 99 and 100 have been drawn from at least 5 such pieces of regulation. The first step, textual representation, involves development of structured English rules from the aggregate collection of relevant laws, regulation and road rules. These structured English rules take a 4-part form similar to computing's if-then-else logic, with the addition of an exception clause that triggers the then action. If these qualifiers and elements are true, except where this other qualifier is also true, in which case then you take this exception case action, else always perform this general action that is applicable to the vast majority of situations and circumstances. So, for example, in Rule 2, we see that if the occupant is a minor and they're under 3 years of age, except where the vehicle is a taxi and the correct restraint is unavailable, then the minor can be unrestrained, else the correct child restraint must always be used. The plain language structured English approach supports the second step, mathematical representation, by enabling variabilization of rule qualifiers and elements and the creation of Boolean equations that algorithmically represent the structure, flow and result of each rule. Finally, review of the law, rules and Boolean equations enables the third step, visual representation, by supporting construction of law maps. Law maps visually represent the intention, requirements, flow and decision-making processes that are embodied in the law and can assist both lawyers and non-lawyers to more easily understand how a given law works. This law map represents the simplest view of the legislation that Road Rules 99 and 100 were drawn from. To support our contention that these representations enable construction of AI, we used the 3 you just observed in development of a Bayesian network model capable of reasoning UK seatbelt law. When provided with observations based on potential scenarios, this model correctly reasons the legal seatbelt requirements and shows the result in the top left node. This particular example demonstrates that a child between the ages of 3 and 14 who is under 1.35 metres in height may ride in a vehicle that does not have a suitable child restraint available, but only where there is an allowed exception to the general rule that a seatbelt must be worn. Such an exception occurs when the journey is to be undertaken in a licensed taxi or hire car, or in a situation where a short journey of unexpected necessity is required. Say, when an extended family member is taking the sick or injured child to hospital in their car and they don't have young children of their own or booster seats available for the child to sit in. Returning to the Department of Transport's proposed monitoring tests, we decided to find out whether the ADAS and autonomous systems in current vehicles were actually capable of compliance with the UK road rules. The 3 top-spec current model vehicles shown here were used to test adherence to 23 different road rules. Each vehicle was supplied with a large number of factory-fitted technologies, the highest specification being the SAE Level 3 BMW, which came with their Driver Assistance Professional package. This package was a system that could perform fully autonomous driving in low-speed, high-density traffic, such as a traffic jam, while also being capable of driver-monitored but largely autonomous highway driving. Our 3-step approach to deconstructing each item of traffic law was extended to include 2 additional technology-related steps. Step 4 seeks to identify and document the manufacturer's technology response relevant to that law, and Step 5, in which we assessed whether that technology was compliant to the law in both simulated and, where appropriate, real-world traffic conditions. As we saw before in the structured English rules, UK traffic law prescribes the wearing of appropriate restraints. Seatbelts for adults, booster seats for children, and child seats and capsules for the smaller children and infants. Using pressure sensors in the seats and circuit detection in the seatbelt fastener, most modern vehicles are able to indicate with visual and audible warnings when a seat is occupied and the seatbelt is, or has been, unfastened. In our tests, the only vehicle with individual occupant sensors on each rear seat was the BMW. When a rear seat occupant in the Mitsubishi undid their seatbelt, a chime was heard, but the dash indicator did not indicate which specific occupant was responsible. On the Vauxhall instrument cluster, the 3 rear seats appeared, and the specific seatbelt that had been undone was indicated in red. While in the BMW, occupants with their seatbelt correctly fastened turned green, and if they undid that seatbelt while the vehicle was in gear, that individual flashed in red. None of the vehicles was able to identify whether the individual was an infant, child or adult, meaning none was capable of ensuring whether the appropriate capsule, child seat or booster was being used. Drivers are required to inform other road users, in plenty of time, of their intention to change course or direction, effectively to indicate when we're going to stop or turn. We must also be alert for the same signals of others and respond accordingly. Finally, we must yield to the signs or directions of police and traffic wardens. Many new vehicles, including the Vauxhall and BMW in our test, include a traffic sign detection system that uses cameras at the top of the windscreen and hard-coded AI to read and alert the driver on the instrument cluster and in the heads-up display to changes in speed limit or when they should give way or yield to traffic. For each, we show examples of traffic signs that the manufacturer's literature claims their vehicle is capable of recognising. Above each, we show whether that sign was consistently identified during our road tests. While all 3 vehicles were capable of identifying and warning drivers when another vehicle directly ahead was slowing or stopping, using the forward collision mitigation system, none was able to identify the signals of those vehicles, such as the brake or indicator lights, and respond accordingly. Further, in situations where a school crossing warden was holding a stop sign, the BMW, which is the only vehicle that should have identified the sign, incorrectly indicated a small hatchback vehicle in the path of travel. In totality, the ADAS systems of none of the 3 vehicles in our test was able to even contemplate the requirements of Road Rules 103 to 105. Lane markings indicate the borders within which we're supposed to maintain the vehicle. They also indicate a wide range of other lane-related rules, including where we may enter or exit the lane and whether we're allowed to change lanes in order to overtake slower moving traffic. 2 vehicles in our test, the Vauxhall and BMW, included a lane-keeping system for warning the driver in situations where their vehicle may stray across and into another lane, and both were capable of automated steering in order to return the vehicle to the centre of its own lane. While both vehicles correctly identified lane markings and the lane-keeping systems generally performed flawlessly, even when markings were faded or in poor lighting or during mild inclement weather, we found neither alerted the driver to situations where they should categorically not cross the lane boundary, such as circumstances where single or double solid lines indicated overtaking was not permitted. In every case, both vehicles failed to alert the driver that they were performing an unlawful manoeuvre. A further issue was identified with the BMW system. Its driver assistance professional, which was capable of monitored but largely autonomous driving, including lane changes when prompted by the driver using the indicator stalk, was willing to cross in unsafe and unlawful situations against even double solid centre lines. Overall, this work has reviewed the legal background for automotive design, materials, manufacture and driving law. We've discussed the technological systems and a taxonomy for how we classify their presence in the autonomous vehicle. We've demonstrated that it is possible to deconstruct traffic law for use in creating tools that enable integrating the rule of law in the development of autonomous vehicle systems and AI, for which we presented a Bayesian network model that reasoned the appropriate lawful seatbelt requirement. Through demonstration of that BN model, We contended that these tools are capable of supporting validation of the operation of that law in the decisions that the AI makes. And finally, we reported on a few of the road tests conducted to evaluate whether existing vehicles with ADAS and autonomous systems were capable of adherence to UK road traffic law. In the paper that we've prepared for publication that further describes this work, we evaluate operation of the vehicles and their various technologies across 23 of the UK's road rules. We show that adherence is still an issue for most vehicles and in many situations. We also argue that the wholesale importation of existing road rules as a model to govern autonomous cars may at best be unreasonable, and at worst, impossible.